Hi, good afternoon, everyone. I'm Janice Oliva, president of ISE Magazine, and we're so glad to have you here today for ISE's webinar entitled Fiber to the Antenna Primer, presented in partnership with Brigade. So before we get started, though, I would like to remind everyone, if you don't already receive ISE Magazine in print or digital format, please sign up for your complimentary copy of ISE Magazine. We're the how-to resource for ICT providers across the globe. And the link is on your screen as well as in the information tabs of this webinar. It's complimentary for those who are involved in the industry and a great resource of information and up-to-date data and statistics and case studies. So we hope you'll take advantage of that. Also, we have our ISE Expo coming up. So please make sure to register for this one coming in Denver for 2018. It will be held at the at the Colorado Convention Center in Denver, August 14th through the 16th. For details on all the educational sessions and the exhibitors that will be participating and at the show, please go to iseexpo.com. And you can learn more about that and register there as well. And if you go there, please ask for me, look me up. I'd love to meet you in person. And be sure to visit our ISE Buyer's Guide online. We've gathered all the great data and we've categorized it for you. We've got the latest products for wireline and wireless just for you for your buying needs. If you just go to isebuyersguide.com, you're going to find exactly what you're looking for in an easy format, and you can get to it today. So in addition, we've got a great sponsor with us today, a very consistent supporter of ISE, Brigade. Brigade has instructed more than 50,000 attendees in its public and custom classes since 1987. The company offers a variety of fiber optic courses that cover basic fiber optic design, maintenance, and testing, as well as more advanced topics such as fiber characterization and FTTX. They also provide course development services and will custom create a course to any fiber optic subject matter or skill level. In addition, Brigade produces professional quality educational DVDs and online training. All of Brigade's training materials are technology-based and demonstrate theory and techniques applicable to any manufactured products. So now let me please introduce you to our esteemed presenter, Phil Shoemaker, who is a senior instructor at Brigade. We're so happy to have Phil with us. He's been a member of Brigade's training staff since 2000. And his work with fiber optic technology includes the design, installation, and maintenance of fiber optic voice, video, and data communications networks. And he has also participated in troubleshooting and emergency restorations. He has a Bachelor's of Applied Science in Electronics Engineering Technology and is certified as an ETA Installer Administrator, a NARTE Technician Class 3, and has FCC GROL certifications, Elements 1 and 3. So he's got a lot of background and a lot of expertise. I think you're really going to enjoy hearing from him today. So before we get started, though, I do have some logistics that we'll want to cover so you guys can take have the most advantage of utilizing the tools within this webinar format. At the top, there are information tabs that you can access more information about our speaker and our sponsor background for the company. The event resource tab on the left side will allow you to download a copy of the slides from today's presentation at any time during the webinar. And finally, you can submit questions throughout the presentations, which we really urge you to please do so. Anything that comes up in your head, please type that into the Ask a Question tab over there on the left, you'll see as well. And we're going to hold these questions till the end, at which time we're going to answer as many as possible. However, if we don't get to your question, we will take your contact information from the registration. We'll reach out to you after the fact online. So with all that, we are finally ready to hand off our webinar to our presenter, Phil Shoemaker. Phil, it is all yours.
Excellent. Thanks, Janice. Hey, everybody out there. Again, this is Fiber to the Antenna Primer. And if you missed it before, again, my name's Phil, and you can see it there on that title slide. Fiber, nothing new to a lot of us out there. Been around for a long time now, but this fiber to the antenna topic has definitely been gaining steam over the last couple of years. And anybody that has their radar out there, looking at what's happening, what's on the verge of new and latest and greatest. If you haven't heard about 5G or microcell or distributed antenna systems or anything like that, it's coming. So you better be aware for it. And even though everybody just sees the antenna part, fiber makes it happen. Obviously, it's the first thing. When you talk about FTTA, it's right there in the title. So with that, we really need to be on our fiber knowledge background with this. And again, this will be the introductory part of it. It definitely can get pretty complicated, but we're going to keep it as primer as possible. Janice already made mention of some of the background with Light Brigade. We've been doing this a long time, technology-based, and our hands-on components are definitely what make a lot of that knowledge come to life versus just a lecture portion of it all. So again, what's driving? So the fiber demand, and this is, kind of the IoT, the Internet of Things, is a big part of this wireless part of it. So it's not just cell-based, and that's what a lot of us see. We see the big macro cells, and pretty soon it's going to be micro cells and nano cells and pico cells and femto cells. You'll hear all these terms when you start talking about the Internet of Things. But really some good statistics here about how many people. I bet you everybody out there now has a minimum of 2 or 3 wireless devices, basically. So with that, we drive this. There's actually more devices per people out there on the planet in a lot of applications. So with that, it's a huge topic. And the more we want this gigabit demand, it has to be fiber driven. So the numbers there speak for themselves, obviously. So again, over nearly 2 billion, right, Facebook users, and most, again, that's not, it could just be on your own PC, but how many people, when you walk around, look at who's got their face in their phone. With that, it's a big deal there that they have instant access to everything. They're totally connected, and again, fiber enables all of that to happen at that point. And talk about the photo uploads and videos and YouTube and everything that happens there with the fiber is that fiber enables all of what you're seeing there to happen, and it's in the billions. And we're literally up into the exabits of global downloads in some of these time frames. So it's a very, very important topic, and you want to be on the cutting edge of all that. So the growth of fiber to the antenna, if there's historically, you've watched these towers go up, and we had basic analog cell phones, and it went up to 2G and 3G. Now we're in our 4G LTE, and there's going to be enhanced 4G. We've watched the fiber get closer and closer to the antenna. It used to be fiber was just the backhaul at the central offices, and then it was a T1 line to the base of the antenna, so it was still twisted pair. Then it was fiber and still coaxial up the antenna, and now literally it's fiber right to a module in the antenna. And I've even ran into some customers here recently that the antennas already come with fiber pigtails coming out of them, and you just have to connectorize it, and it's all done. And with that, not only do you get the huge bandwidth, but you also get a huge advantage of tower loading and the wind and all the environmental effects that all of that heavy copper cabling would cause on those towers. So there's tons of benefits when it comes to the fiber going to the top of the tower at that point. Bandwidth being the foremost of all that, but there's also a lot of structural elements that fall into it as well. So here's some terms that I was just bringing up at this point, and we're seeing, and here in some of the pictures, we're seeing actually a DAS head end on the bottom, and this is also going to be a big portion of what's going to happen in the 5G world. It's a whole different, it's completely different frequency. The coverage will be far more dense. It's a different wavelength and or frequency. It won't have the same penetration into large buildings and structures. So moving those signals inside of a DAS head end like we're seeing here on the bottom left will take those signals from an antenna and then distribute it through the building through another set of antennas. And we see that bullet there is the DAS, distributed antenna systems basically. And then working our way through some of these bullets, obviously macro cell, that's the one we're most familiar with. You see a slide there on the right-hand side. That picture is one of the ways they'll do fiber to the antenna. It's a pre-made antenna array. Fiber was already in the telecom world. We call that a splice closer. In the antenna world, they call it a squid. More, I think, by how it looks than its function, basically. But at that point, it's all pre-built, and then it was all hoisted to the top of the structure at that point. That would be the macro cell. Micro cell, you might even already have those around. If you look on your light poles and smaller utility poles, and if you have the aerial plant, you'll already probably see some of these in more of our dense population areas. Small cell, again, that kind of brings it into the buildings, and then pico cells and femto cells. This will be much like your Wi-Fi routers you might already have in your house or office. Though they'll be transmitting cell transmission instead of the Wi-Fi. So it's very similar to the products that we're already comfortable with. But that is, and then the HetNet, the network there is basically kind of a combination of everything. The wireless, the cell phones, it's just a broad term on what we see and use for fiber to the antenna as a whole. So you'll also see the term HetNet come up there quite a bit. So again, why fiber? Why do we need this for this next generation? So speed is the game at this point. And latency. That's another big thing you're hearing about in a lot of these new systems. We won't see much of it here, but in some of our other antenna applications, we talk about what we call the cloud remote antenna networks and the CRAN, basically. That requires very, very low latency, millisecond latency, and fiber provides that option to us, and then unlimited bandwidth. If you aren't aware that single mode's capabilities, the fiber that is feeding these antennas, unlimited bandwidth. Maybe someday we'll reach the point where electronics can find the limitations of single mode fiber, but as it sits now, the antennas that are to be installed with single mode fiber now will never run out of capacity as far as the bandwidth goes on the fiber. Go up and change out a couple of modules on the antennas, and now we're rocking and rolling for the next generation of applications. And so again, we talked about what was acceptable for older 3G and older analog networks. Those systems are no longer capable of supporting what we see coming down the road. So the network has to be upgraded to support what they envision happening in the very, very near future. So some advantages of fiber. So obviously I was talking about the bandwidth, and I can kind of see that on the one of the bullets there. Low loss. Fiber, when you compare it to copper conductors, just loses tenths of a dB per kilometer. And then in some of these cloud CRAN type of applications or centralized remote radio access networks, basically, they can be upwards to 20 kilometers or 13 miles away, because the fiber itself is so little loss. You can put all the electronics in one centralized location, run up to 20 kilometers of fiber to the antennas, and it would work just like all the equipment is sitting there at the antenna. So the low loss plays a big part in these next generation applications. And then the noise immunity. Fiber is immune to all electromagnetic and radio frequency interference. So imagine all of that radio frequency, all the noise that happens up there, not only from the 4G and upcoming 5G antennas, but also when you look up there too, you'll see a lot of microwave antennas basically receiving, then retransmitting microwave signals from that. Instead of having to do landlines, they can still use the microwave to get that signal to where it needs to go at that point. Copper systems highly affected by all of those signals and power levels, fiber completely immune. So huge advantage there. So also made mention of this right at the beginning of the presentation, the actual power loading and pole loading that happens with fiber is nearly minimal. That it's small size, lightweight, and also I just ran into some customers that talked about the wind loading that will happen. We have a large array of copper cabling that actually creates like a sail essentially on these large towers, where fiber, one fiber cable could take place and replace all of those copper cables, all that coax, and save the structural issues that they've found with some of the heavier and larger copper cabling. Fiber offers a level of security you just don't get with other media. It doesn't emit anything. Not 100% secure. These are some things we can see. It is tappable, but once you tap it, you can be detected that it's being tapped. But since it doesn't emit anything, it's a very difficult process to tap a fiber system. Fiber covers a very wide temperature range, down below zero up to about 160 degrees Fahrenheit for your off-the-shelf applications. It does even go hotter and colder. So if you were working in some harsh environments or had some of these antenna arrays that I see up in Alaska and down in the deserts, that they do have fiber cable and cabling meant for those conditions as well. So it is not affected by those applications at all. And then it looks like in some of our images there too, you're actually seeing what we refer to as some hybrid cable. You can run your fiber and power, low voltage, high voltage, whatever it needs to be, all within the same cable structure, thus saving loading and weight on the tower as well. That was actually one we're seeing there in the bottom left, that yellow cable. Looks like it's a hybrid cable, so it has power for the antennas and fiber for the data all in one cable structure, which is fantastic. So what kind of fiber would we typically see in an antenna application? So generically, single mode fiber. So the single mode fiber is, again, the one with unlimited bandwidth and very low loss. We're anywhere from 0.4 to 0.25 dB per kilometer, depending on the wavelength. So up to the tower, we typically see the ITU, we're going to be referring to the ITU-T standards. So the G.652 or 652D would more than likely be what you're using up to the tower application. The D would be the low water peak or zero water peak single mode fiber. And this would allow for future growth and a technology we call CWDM, or coarse wavelength division multiplexing, would happen with that 652D. Now, on the tower itself, you may be encountering, tight bend radiuses or certain clamps to secure the cable. So the cable itself may fall under some what we refer to as extrinsic stresses, micro and macro bending. So with that, it's highly suggested to use one of the G.657 families of fiber, generically known as bend tolerant or bend insensitive fiber. This is an amazing fiber that is not brand new, but it's the newer of the single mode family that has a special layer around the core itself that allows for, I've seen it down to 5 millimeter bend radius, and it still physically works without any negative effects. So it's really amazing when they get into that. So when you have these tower climbers and people not necessarily fully trained in fiber optics, they can install this, and it works great as long as it's all secured and cleaned, and we're going to see some of that here in the later slides. So here's a slide just on the 652 and 652D, and again, that falls under the ITU-T standards. And so instead of calling it by a particular brand name, this is generically what we would refer to this fiber as. And again, that makes mention of the coarse wave division multiplexing. If you look at the 652 fiber, let's say on an attenuation chart, you'll see what's referred to as a water peak between the 1310 and 1550 transmission windows. And the 652D method, they've reduced or eliminated that water peak, so it allows for a large range of wavelengths, up to about 18 if you wanted to fully utilize the full CWDM spectrum. And so for future growth, that's a great application. when fiber grows, when the demand for bandwidth goes up, you have two options. You either add more fibers at whatever cost that could be, or you add more wavelengths to the fibers you already have. And so this is where the wavelength division multiplexing technologies can really benefit in maximizing the capacity of your single-mode fiber plant. And then the 657 fiber. And so we're going to see a little animation here that highlights the bend-sensitive fiber. It's comparing the 652 and the 657 families of fiber. So we'll go ahead and we'll watch this animation, and then once it's over, I'll get through and I'll have a little dialogue about this video once it's completed. So if we could run that video, and we'll just roll with that right now. All right, let's see, that's fantastic. So the animation there really highlights the bend rates, even though not to scale, but it really amplifies how great the new generation of bend-insensitive fibers are compared to just everyday single-mode fiber. There was a time that single-mode fiber was only relegated to long-haul outside plant, maybe fiber to the home drops. But with the 657A and B, B being the better of the group, complete down to, I mean, that serves a 7.5 millimeter bend radius. And again, I've seen it go even smaller with minimal effect on the losses. And again, we're watching these losses at 1310 and 1550 nanometers with zero effect. So it's quite an amazing thing to see on that. All right, so let's see here. So now with this, we also have the option of having several different cable designs. So the fiber itself is wonderful. Obviously, that's what we're talking about here, but pretty fragile. So you need a way to protect that between wherever you're going, basically from point A to point B. And so most of the cable running up to the antenna, and again, we can typically see this in a variety of lengths. 20 kilometers is about the biggest you're going to see in the C-RAN applications. But if it's just feeding directly from a central office or a head end somewhere, it could even be longer. We've seen distances of generically up to about 80 kilometers, 50 miles or so with minimal losses. But again, the latency effect is something that we may see as the speeds gain in future growth of the antenna applications. So the bottom one you're seeing there is generically known as loose tube cable. And so it can be anywhere from 1 to 24 fibers and a tube. The tube is usually 2.5, 2.8 millimeters in diameter, upwards to 3 millimeters diameter. And then there's going to be some sort of water blocking agents inside of those tubes. So historically, you may actually hear somebody call that loose tube gel fill, but the gel has been slowly filtered out. You're going to still run into it though, but most of the newer stuff we've seen can historically be just loose tube at that point, and dry, 100% dry, outside the tubes and inside the tubes. Now, the two top examples are what we generically refer to as tight buffered. And the tight buffered is a second coating layer that tightly packs around the fiber, and it helps waterproof it. And then the two options we have here are what we call a breakout cable, which is the middle cable in the black jacket, and then a distribution cable that is in the yellow jacket up there. Really depends on the application and what the customer wants. We've seen loose tube cable going up the tower. I've seen breakout cable, and I've even seen distribution cable going up the tower. They would all be a viable option depending on what the tower owner and or customer wanted for that application. They all have the same single mode fiber in it. It could be the 657A or 657B inside that cable, and it would work great. And then again, if the customer wanted to combine power and fiber in the same cable, at that point you'd have the hybrid application, which would be wonderful. So the reason for the two cable designs. So here we have the tight buffered on the upper right and the loose buffered there on the lower right. The loose buffer, so in the outside plant, your cable is going to go through lots of expansion contraction. A lot of us live in parts of the country where you might see a 100-degree temperature swing in one season. And so in those below freezing applications, the cable will shrink. And so at the bottom there they have the animation or the picture C, basically, the cable shrinks and the fiber stays loose and protected inside of the tube, again, protected by a water-blocking powder or gel. In the summer months, the cable relaxes. And so when the cable relaxes, again, that's what we're seeing there. And then it also stretches during installation. We're seeing that there in option B. And then as manufactured there on the picture A, it's just kind of sitting there loose and on purpose as it is. So that's the main reason. Now, the tight buffered option for a backhaul, or even what we hear here in the fiber to the home world called the front haul up to the antenna, the tight buffered option, the fiber itself does not have a whole lot of thermal expansion. So what you'll see typically is all the tight buffered coating there, which is up to 900 microns, and it might be a Kevlar overlay, then another maybe PVC jacket on top of that. It does not expand and contract a whole lot as the plastics do. So it can go under much undue stress for a long haul system. Again, if it's just up in a tower, both of those options, tight buffer and loose buffer, would be a viable option. Like I said, I've seen all of those here recently. It just depends on what the end customer wants at that point. Nice example here for composite and hybrid. Now, this is where the terminology gets a little messy. A lot of what we do, a lot of our telecom folks, they like to do, especially with our building applications, our premise applications, they follow NEC. And NEC has these terms, basically. They'll call it composite, which is seeing there, and it's all listed there under NEC 770.52. Unshielded twisted pair in fiber, coax in fiber, power signal in fiber. So basically we have conductors and fiber all in the same cable. They'll refer to that as composite. And then they would call hybrid something that would have single mode and multi-mode in the same cable. And then we get into other industries, antenna being obviously the one we're talking about today, and they will call that composite cable a hybrid. So when you look at the fiber to the antenna cabling standards and other papers that have been written about the antenna installations, they're going to call those cables, everything's going to be called a hybrid. And there really isn't a need to have a mix of multi-mode and single mode. So it's all going to be single mode up, and then if power or conductors are in there, then at that point you would be calling that a hybrid cable. So like I made mention, the reason, one of the big mentions and needs for 657, the bend insensitive fiber, is because we have to attach it to the tower. And it's got to be clamped typically every 3 to 5 feet. They're going to be usually large rubber grommets that are attached. And you can look at any of the tower equipment suppliers, and they're going to have a wide variety of clamping products. Just make sure it's designed for the diameter of the cable. Fiber cable is going to be historically much smaller diameter than a larger coax cable. So with that, you want to make sure that you have something that's made for fiber. And as fiber becomes more prevalent in the workplace for this application, there's going to be a wider variety of products available for the installers, for the tower installers at that point. One of the things we see on this would be pre-built. You're not going to find versus telecom. We'll do a side-by-side example here. So an installer does a fiber drop to your house. They're going to do a drop cable. They're going to fuse and splice on a pigtail at the home with a proper connector, and then put it in a splice closure, and then it's in a panel at your house, and it's ready done. I don't see too many people up 100, 200, 300 foot off the ground with a fusion splicer, regardless of how small it is. It's just going to happen. So the antenna market is really big on pre-terminated cables. And generically, again, it came along with the fiber to the home market, hardened connectors. We're seeing a great example of a hardened duplex LC on the left, single mode by its color. And then we're seeing an MPO connector on the right-hand side. So the MPO, the multiple fiber push-on, are ribbon-style connectors. So what you're going to find is upwards to 12, 16, even 24 connectors could be put in one of those MPO, 12 being the most common in current market here. So, and we're even seeing an increase there on the LCs even though we're showing the UPC polish, and we know that it's the UPC polish by its blue color, an increase in LC APC polishes. Again, it all depends on the equipment manufacturer and what kind of signals are going to be running over those fibers. But again, all pre-terminated, and we're going to get into some pros and cons of that. And then again, it talks about the ratings they should be. So again, the harsh environment, or what we call the hardened connectors, need to meet IP67 or IP68 requirements for, you know, spray and water and resistance to the elements, because they will be in a harsh environment more than likely. Now, at the base, you have all kinds of termination options, and so the pigtail splicing I just mentioned for a fiber drop is still a very popular means of terminating it at the base. So you could use a low-cost fusion splicer, you could use a high-cost fusion splicer. It wouldn't matter at that point. It would just be splicing pre-terminated ends to the incoming single-mode cable. You can buy pre-terminated modules, so the connectors are kind of, it's a pre-done. There on the right-hand side, that polymod is basically done with pre-made pigtails for you, and then you just run your cable into that. It's still essentially pigtail splicing, and then the patches and whatnot can all be pre-terminated. So the cable incoming typically would not be pre-terminated, so that would still be spliced on. But the antenna cable, the actual tower cable, could be terminated on both ends as long as it was ordered properly with the right length and the right amount of slack and everything. Both the base and the top would be pre-terminated. Now, beyond pigtail splicing, there are some other options out there. Now, we typically would never recommend, for those of you that have been in the industry a long time, you'll say, well, I remember a day when we used to hand polish single-mode connectors. Well, that probably worked 20 years ago. In today's world, with the low loss requirements and especially the reflectance requirements, the optical return loss requirements, hand polishing single mode is no longer even talked about or even required at that point. So there's lots of options beyond the pre-terminated options on the cable. We have a variety of splice-on connectors, and they can be fusion and or mechanically spliced. Again, typically for base locations, and they can come in a variety of connector styles. But again, typically your LCs and FCs will be found at the base, but there's also MPO options as well. So regardless of what kind of connectors you have at the base, if you didn't have room or didn't want the pigtail splice option, definitely look up some of the no polish or splice-on connector options. Those are all just as good as anything you can get from a factory-made cable at that point. So again, back to the pre-terminated assemblies. So again, the installation is much quicker because everything's already done from the factory. The one image I showed towards the beginning of this presentation showed the pre-terminated. The whole antenna was done on a trailer. Cable was already there. Connectors were already up the squid. The cable was already up the tower. So these climbers went up and they hoisted up. They had a big winch coming off the back of the truck. They hoisted up the antenna and just plugged it in. Now, I didn't stick around. I wasn't watching them from the base to make sure they were cleaning everything properly. We're going to see that here in a bit. That's a big part of this topic. But it did save a ton of time that they didn't have to do all of that physically hundreds of feet up in the air at that point. So again, yield is the name of the game for connectors. So the higher the yield, the better the results, the less work time, the less labor. You're going to spend a little bit more on the front end for all this pre-terminated products, but it is well worth it in the labor savings at that point. Now, testing. All right, so there's a few things a little bit different in testing the antenna, though it's still simple. Optical loss testing and OTDR are the two primary ones. We're still going to clean, we're still going to visually inspect, but the one big effect that we're seeing that is happening out there is because these installers think this is a factory-made connector that still had caps on it, they're going to take that cap off and simply plug it in. And it's causing damage to connectors. We have high reflectance, high loss, if not physical damage, and which we then see when we physically come and test these. So there's a lot that goes into the testing part of it. And then we're seeing a variety of testing requirements depending on whose tower, whose antennas they are. So the major providers, some require just optical loss testing, some require OTDR, some require loopback testing, some require video inspection proof, you know, the video cameras and taking the picture and sending all that back in the report. So the more, the faster and the more detail that needs to be done to these installs, the more requirements we're going to see on the testing side of all of this. So first and foremost is connector inspection. And this isn't simply the handheld inspection scopes that we all may be familiar with. The problem with that is it's very technician subjective on what is a pass or a fail. So the international community under the IEC standards have created this automated test, and we're seeing that it breaks your connector down into 4 zones: the core, the cladding, the epoxy, and the contact zone. The software physically analyzes the end face of that connector and gives a pass-fail results based on international standards, not what a technician thinks. And so there's no doubt whether that's a good or bad connector. And we do this to every connector every time before we plug it in. And not only look at what we are handling, but also what we're plugging into. Because there's if you've heard the terms UPC and APC polishes on single-mode connectors, the PC is for physical contact, and that's the reminder that when these connectors come together, there is a physical contact. And the glass itself is relatively soft compared to the ceramic ferrules and other materials we have out there. And if you have any corrosive materials on that glass, abrasive materials, you're going to scratch and pit that fiber, and then that whole pre-terminated cable assembly now isn't any good. And guess what? It has to be reinstalled at some point. So it's very, very important, paramount, that that is done properly and inspected properly. So here we have a technician. This would be more at a base type application. He's using a version of a video inspection probe. And these have made some amazing strides over the last few years. They used to be full, big, handheld, isolated units. And then they got to where they had their own little screens. They looked like little cell phone screens, but there's still a proprietary screen and software that the probe hooked up to, or it was laptop-based. It was a USB probe that went into that. Some of the newer ones are Wi-Fi and Bluetooth enabled, and it goes right to your device. So now your phone is the inspection equipment, and there's a lot of great apps that would run those devices through all the people that make that equipment. And then anymore, there's even ones that will in real time take that and load it to the cloud in real time. And so the people in the office and the managers and designers of these systems can see what's happening in real time, so the people in the field can be aware of something that they maybe missed. So there's more eyes on this versus taking everything back to the office and then filling out the reports, and then they come back a week later and say, oh, yeah, that connector up there, it's no good. So we now got to pay a climber to go back up and do all that. And that can get pretty expensive pretty fast. So all of this will help reduce labor and downtime all in the same shot at that point. So you're seeing a couple varieties of, again, these digital scopes, one that's actually hooked up to the OTDR. So your OTDR anymore can be your optical loss test set, could be the OTDR and inspection all in one shot. And then we're seeing another smaller handheld version there that would be a Wi-Fi version, screen built in, but it also would transmit it to a handheld device as well for storage and transmitting and a lot of great features at that point. So the main thing here, there's a lot of reasons why we prefer the digital scopes. Obviously, pass-fail results, that's big. Safety, paramount there. If a technician accidentally looks into a live fiber, they won't necessarily realize it's a live fiber with a handheld scope because we're in the infrared spectrum. So with that, this is a great safety tool. And then the other thing is we have the right adapters. We can see inside of the bulkheads. We can see inside of the modules. And so we can see, like the transmitters and receiver modules, we can see physically inside of those what we're plugging into and verify that everything's clean at that point. So we inspect. Now, if we inspected something and saw that it was dirty, the first thing obviously we're going to clean. We prefer to use some sort of dry cleaners, and so we can see that the cleat top is one of my favorite tools, especially if it's just a patch cable or a connector or something that I can physically get a hold of that connector and wipe it down. Now, if I can't get the connector to the cleat top, I'm going to go to my next favorite dry cleaner, which would be a version of the One-Clicks. And they come in LC and SC or 2.5 and 1.25 millimeter tip sizes. And so the dry clean is the preferred way. Now, if we get into that and we dry clean it and nothing looked like it was cleaned, we may go to a wet clean. We may go to a wet. Maybe we have some crusty, hard contaminants in there, dried-on contaminants. And so we're going to go ahead and wet clean that and then inspect it again. And then we're going to dry clean it. And so you always want dry to be the last cleaning you do. And so sometimes it's a multiple step, and it's very, very possible the first clean you do will not be the last clean you do. So, and you definitely want to inspect after that. So there's a lot that goes into that, and there is just a full catalog of products for all the cleaning. But that, in upwards here, I don't think we have the numbers here, but you can go a lot of studies, a lot of studies out there, approaching 80% of all fiber failures, and an antenna is probably going to be even higher than that, can be related right back to contaminated connectors. Even from the factory, they can be contaminated. So this would be the very first thing to check, not only during the installation, but during any troubleshooting. That's where we start. So here's that term we talked about earlier. There's the squid. Again, in the telecom world, we just call that the closure, and it looks very similar, dome-style closure. These would come pre-terminated with the LC connectors, and you can see that the one on the left, the base of it is off, and you can see that there's a series of LC duplex, single mode, UPC polishes there, ready to accept the pre-terminated tower cable. And then kind of on the right-hand side is what they would look like. That particular installation, they separated power and fiber. So they had fiber in one squid and power in the other squid, and that's perfectly okay. We've also seen them where they're a hybrid squid, so all of that could be physically done in one closure to save the actual tower space. And again, the more things that go up there, the more space is a premium. That's a very good option to have. And then here's a really good shot of a base tray at a base tower. And so here the installers brought the cable in, and you can see the splice tray there towards kind of the middle of the picture is kind of the back part of that tray. And then pigtail splices were done, and these are SC connectors, all pre-terminated at that point. If you wanted to have a more condensed style of tray, this is where we started talking about the Splice-on connectors, where the technician could have put on a fan-out kit onto the loose fibers, built them up to 900 micron, and then fused and spliced on those same SC UPC connectors. And it could have been a smaller footprint if that's what was needed for a particular job. They had plenty of room at this site, so that wasn't an issue doing the pigtail splicing there. And again, you can tell great skill on this one. They did nice color code organization, proper band radius, everything was secured properly. That's what we'd like all of ours to look like if possible. And then the different types of test equipment. So at this point, the OTDR is a really fantastic tool to have. We can do it for basic testing before the cable's installed. We can do it after installation. We can use it for troubleshooting. It's going to find the basic signatures as far as reflective, non-reflective, gain, and roll-off. It's going to do reflection testing for us and overall what we call ORL, or optical return loss. That's the sum of all reflections coming back to that transmitter. And then here we have the most simple piece of equipment, which would be your optical loss test set. So individually, it's a light source and power meter. Together, it's the optical loss test set. So if this is a true transmitter receiver, so if you want to see the actual loss between 2 points, this is the test set that would be that you'd be doing as far as light source and power meter. Now for faulty pigtail testing or troubleshooting or short span continuity checks, the great thing about just antenna applications, again, pretty short runs, we can use the VFL or visual fault locator, usually limited to the 2 to 4 kilometer range depending on the power of it. So if you're just looking up, continuity test up or down a tower or a loopback type of application, VFLs work great. And then back to the inspection scope, microscopes, the video scopes. And another great tool that works on single mode is the fiber identifier. So if you're trying to track a fiber, and it's very, very possible that when it was installed, fibers got moved or rolled, or something didn't get labeled right, the fiber identifier is an instrument here. You can see the technician, he's crimping it on the fiber. And at that point, light is escaping out of that single mode patch cord, and then the detectors within the identifier will then say, I see live fiber, or I don't see any light. Or you can even tone your single mode light source at a 2 kilohertz modulation, and you can tone those fibers out, which is a great way to trace where that fiber physically goes. Now, the version that we're seeing here won't necessarily work on those new bend-insensitive fibers I talked about on the previous slides. So they have a new version that works with the bend-insensitive. So if you are using the G.657B family of fibers, you want to make sure that you're using a fiber identifier compatible with those bend-insensitive fibers. Now, if you're getting into what we refer to as the front haul, so if you're getting into the C-RAN, where you have the remote antenna networks and the 20-kilometer spans with an array of cells, you got to get into new types of test sets, and this is what we typically get into, the all-in-ones. So you can have the CIFRE testing, you can do the CD and PMD testing. So one of the things also that's happening in the antenna world is some of these operators are looking to lease fibers. And in leasing fibers, you want to make sure that the fiber you're looking to lease is going to be compatible with the network you plan on putting on those fibers. So who knows how long those fibers, they might be 30, 40-year-old fibers. Who knows, right? So at that point, you want to do not only your loss testing, but you want to do your ORL testing, you want to do your CD, PMD, and then even the CIFRE is more once the antennas are done, because that actually emulates the antenna protocols to make sure that everything is working properly at that application. So, and then if you need to actually get into bit rate testers and data rate checks and different things like that, that's somewhat secondary. But those top few bullets are definitely important in today's longer antenna applications. Now, loopback testing, not anything new. This isn't a new technique, but it has been brought back into popularity with antenna applications. Again, we do not necessarily like to have thousands of dollars of equipment up the tower with the climbers, because one wrong move and that thing is falling a long ways. So the minimal amount of equipment goes up the tower. So there is loopback testing. They actually make duplex LC connectors meant for optical loss testing loopback. And then we've seen also loopback testing with the OTDR. But because of some of the limitations on the OTDR, much into the dead zone of the OTDR and connectors, they typically would use a 10-meter loopback with the OTDR. So you cannot, so you can see the connectors, recover from the dead zone, and then see the up connector and the down connector essentially at that point. And so those are done with a couple of different methods, but they're a great way to verify not only loss, but return loss and physical loss of those connectors with both, again, power meters and OTDR applications. So here we can actually see the loopback connector there on the right there I was making mention of, and then cleaning and visual inspection. So before we do any testing, again, cleaning and inspection are paramount, and then we physically do the test. That doesn't do us any good to test dirty and damaged connectors. So, so at that point, again, minimal products going up. So just those small pieces of equipment go up the tower, and then the expensive equipment, the OTDRs, power meters, and all that stay at the base at that point. These are a little bit small screens. I couldn't remember. I don't think we have a bigger shot of this here. We may on the next slide. Yeah, we do. So we're seeing incorrect and correct. We're going to see a zoomed-in version of the correct slide here in a second, making mention of just what I talked about with the dead zone of the OTDR. And if you use the wrong settings or the wrong loopback, that top connection will look like one big event instead of two individual events. So if it is done properly, this is a proper loopback with an OTDR. So the very left reflection, the Fresnel reflection, would be at the base using a dead zone box from the OTDR. And it goes up the tower. It sees the first connector. There's a 10-meter loop back, then it sees the other top connector, and then it goes all the way down to the base, and the fourth or the far right canal reflection is essentially the base at that point. So with the proper dead zone boxes and terminators and loopback patch cables, you can analyze basically all your reflection and loss of all those connectors at that point. And it's great for troubleshooting and documentation. And we're actually seeing a little bit of loss, a little bit of gain. And the more you get into OTDR, you see what's happening at the top of the tower. Could be cause for alarm, or it could just be different types of fiber that happens to be used in those loopback connectors at that point. And then again, reflection testing is paramount, especially with these high-speed systems. A lot of things are digital. I have had some customers still using analog transmission. And so at that point, ORL and reflection testing is very, very important. It's at the top of the list beyond what the attenuation would be. And if it's not done right, you might get some results that maybe would throw somebody off. So if a connector is not terminated, here we're seeing in the middle of the screen, we're seeing this very, very high reflection. Goes to the very top of the OTDR screen, and then off to the very right, we have an event called ghosting. And the ghosting there is caused because we have highly reflective events that shouldn't be there on that particular screen, and it causes an echo or a ghost of what we're physically testing. So with proper use of, again, terminator and dead zone boxes, we can eliminate that ghosting and get proper reflection and return loss readings. And so there's a lot that goes into it for troubleshooting, but definitely great things to know. So kind of getting towards the end of the presentation here, and we have basically the things we talked about. Again, making sure you have the right fiber and the right cable, whether you want to do a hybrid or separate power and fiber at that point. Again, make sure that the harsh environment and or hardened connectors are usually all factory compatible with the squids and products that are being used at that point. Making sure everything's secured and cleaned properly. Plan for slack. And again, make sure you inspect everything every time. Making sure you use the right test gear. So again, a lot of these companies in their closeout packages will have very specific test and inspection procedures. So you want to make sure you have the right equipment on hand and know how to use it, basically. And then, again, training everybody on that equipment. There's been plenty of times they've had the right equipment without the right training, and it definitely made a big difference in what they physically saw and what they were interpreting those to be at that point. All right, looks like we have come to our question and answer period. And
great.
Janice, are you still here?
Yep, I am still here, and thank you so much. Those are great slides. I'm a big visual person, so I really appreciated all those really nice visuals and details. Thank you so much. I don't think I'm alone, so I think I said that for most of us. We're going to go into our Q&A right now, so please, if you already have not, go ahead and enter your questions, and we'll answer, like I said, as many of those as we can. So let's start with this one. So they're asking why tight buffered cable is not used for FTTA.
Well, actually, I said they are, so maybe that question was asked before I got to that topic. It is being used.
There we go.
It's all customer specific on what they want to have. I just ran into some customers in the last few weeks that were using a tight buffered breakout cable, and you can also be loose tube. So it's very customer specific, but it certainly can be used.
Got it. That makes sense. Okay, that's probably what that meant.
It just needs to make sure, it just needs to make sure that it's the bend insensitive fiber.
Okay, good.
Yep.
And the next question here is, do you recommend SOC or outdoor environment like at the antenna or outside box? So SOC or, let's see, SOC in outdoor environment. So in an outdoor environment like an antenna or an outside box, do you recommend SOC?
I'm just trying to, so in this term, the SOC, the acronym there?
Good question.
Just want to make sure I'm going to answer it right.
Standard operating cable?
Maybe, I don't know.
No, probably not.
Get more maybe if we can get more information on the acronym, it would be fantastic. But
yeah.
if we're talking about anywhere where we are going to have any, like your pigtails or anything where the cable is not in a hardened connector, pre-built, factory-made, it should always be protected. And I don't know if that was what they're getting at there, but we're definitely going to maybe get some more information and then answer that properly.
Okay, great. Splice-on connector. Thank you, Louis.
Oh, Splice-on connector. Well, there we go. So Splice-on connector.
No.
Well, that's the thing. Now, if it's a fusion splice, so Splice-on connector comes in two formats, mechanical and fusion. Fusion, yes. Splice-on would definitely be cautioned on that because of vibrations and thermal changes. But if it was at the base, the mechanical Splice-on versions would be great. But at the top of the tower, maybe for a quick repair, but then it should be replaced at their earliest convenience.
Okay, great. I do have another acronym, another possibility, which I love about our industry. We make acronyms out of anything and everything, but I have another acronym for that, or another detail for that acronym could also be in a different context, subscriber-owned conduit.
Oh, it could.
So,
it could.
See, we're learning all kinds of stuff.
Great. So,
yeah.
Okay, so any more questions here that we should
get? We do. What is the Fresnel reflection for fibers? Did I say that properly?
Oh, the Fresnel reflection. Yeah.
Fresnel reflection.
The Fresnel reflection is the effect that we'll have with any mechanical interface, in this case, the connection. And the purpose for having specialized single-mode polishes is to reduce those Fresnel reflections. In high-speed digital and analog transmission, that is what will definitely kill the signal. So at that point, the Fresnel. So on the OTDR screenshots, we have the big spikes we saw on those screenshots for the OTDR. Those are Fresnel reflections, and the higher the spike, the worse it is for the signal.
Right. Okay. Yeah. All right, great. Let's see here. I'm looking, and we've got another one here. Why is a 10-meter patch cable needed for OTDR loopback testing?
So we had that one shot that kind of showed a correct way to do it. Now, one of the limitations of the OTDR, as great as it is, it has a dead zone. There's an area after every event where it cannot see anything. And so that long loopback cable allows the OTDR to recover from the connector dead zone and then see the actual loopback. If they were too close together, they would all look like one large event instead of two individual events. So that's the reason for the long loopback for OTDR testing. Now, if it's just optical loss testing, light source and power meter, you can use the little tiny loopback because it doesn't have a dead zone. It doesn't matter.
Yeah, those lovely dead zones. Those are like the albatross of our industry, right?
Well, they can be a challenge, especially on these short runs.
Yeah, really. Those are the worst. And you're like, what's going on? Why is this happening? Okay, we've got another one here that just popped in. Is 50 UM, OM3, or OM4 fiber used, and what would its purpose be?
So the 50 micron OM3 and OM4 fibers are generically known as laser optimized fibers and multi-mode. And what we've seen is probably 15 years ago, we may have seen the 50 micron multi-mode fiber in antenna application. But as they've moved up into the gigabit and then futuristic speeds, the 5G applications, we're not seeing, for the outside, not much multi-mode fiber. Now, it could be used in an indoor DAS applications as long as the length wasn't too far, the bandwidth wasn't too high as far as the demands of the network. All multi-mode fiber is bandwidth limited. So as long as it's been designed properly, then it would work for the current applications, but it may limit growth where single-mode fiber would have unlimited growth for future applications.
Okay, thank you very much. Thank you for that. I'm going to do another question real quick, and I know we're kind of coming up on our hour, and I want to be respectful of time, but this one is, okay, why is the OTDR testing required in a closeout package?
Good question. So the optical loss testing is fantastic. It'll show you end-to-end loss through the loop back and, you know, light going up, hitting the connectors and coming back. But what it may show you have the right amount of loss for that span. But an OTDR would isolate that every component in the span is meeting the spec, not only for loss, but also for reflection specifications. So it gives us a more detailed view of what's happening versus just the optical loss test.
Okay, excellent, excellent. It is 2 o'clock, and I know we all kind of have that hour lunch time. So I'm going to close out, but if you do have any additional questions, Phil, I'm going to ask you to just kind of pitch out your email address, if you would.
Sure, it is pshoemaker@lightbrigade.com, and I will be happy to answer anybody's questions. And also, if you wanted to get way more information on this, I'm going to also be at the ISE Expo in Denver coming up in August. So I hope to see a lot of you guys out there. I'd love to meet with you. Exactly.
And his email is also here on this slide, so you can access that as well if you need to later. Again, thank you so much for attending today's webinar, joining us. Stay tuned for more information on upcoming ISE webinars or podcasts at isemag.com. And remember, every time you learn something new in our industry, you're investing in yourself. So I hope to see you at ISE Expo in August. Thanks for being with us.